Hello and welcome to my second lab report for Physics 2211. Today I will be analyzing the motion of an object falling under the influence of gravity and air resistance. The goal of this experiment is to compare the observed motion of a paper ball with the predictions from two computational models. The first model accounts only for gravity, while the second includes the effects of drag, which is expected to play a significant role in the case of slow falling objects like the paper ball. For the experiment, a crumpled ball, our system, was let go from a certain height. In this way, the Earth, which exerts a gravitational force on the ball, and the air, which applies a drag force as it resists the motion of the fallen object, are the surroundings for our experiment. The foundation of our analysis is Newton's second law, which tells us that the net force acting on an object is equal to its mass times acceleration. From Newton's second law and its relation to the momentum principle, we can derive the velocity update formula and the position update formula. Moving on, this law will be applied to two different scenarios, one where the only force is gravity and another where both gravity and air drag are considered. Another formula we will use is the gravitational force, since our object is being affected by the Earth's gravitational pull, and the drag force, which is proportional to the square of the object's velocity and acts in the opposite direction of its motion. To find the proportionality constant B, we used this equation. We used C to be the drag force, the drag coefficient, the density of air, and A, which is a rough estimate of the area of the object facing the fluid. Plugging these values into the formula, I found B to be approximately 0,00305468. Using Tracker, I captured the motion and extracted position time data for further analysis. We observed the initial position, time elapsed, and since the paper ball was dropped from rest, we know that its initial velocity is 0,00 and meters per second. The y-graph is exponentially decreasing due to the effect of gravity on the paper ball. For the first computational model, I used a starter code and set the initial data, the paper ball's weight, its initial position, and initial velocity, which were shown in the previous slide. I set delta as 1/59.71 because that was the frame rate of the recording. I set the drag proportionality constant to 0 so that the only force acting on the body is the force of gravity. I plugged the force of gravity's formula, and then using the velocity update formula, I calculated the final velocity and used it to calculate the ball's position in each time step. For the computational model that also considered the drag force, I used a similar code, but I changed the proportionality constant to the value that I had already calculated, and I also included the drag force formula and included it in the net force. With all of the data, I created this graph which compares the observed data with the two computational models. Results show that both models predict a much faster ball. However, as time goes on, the model that includes drag becomes a little closer to the ball's actual movement. In any case, there are some clear discrepancies between the models and the real-world data. For the model that considers drag, this may be because the ball didn't fall perfectly straight, but deviated along the x-axis, and this horizontal motion was not accounted for, which likely affected the drag coefficient B, leading to an underestimate of the ball's position. Additionally, the position tracking relied on blurry images, which could have induced some errors. Finally, the drag constant B was an approximation, and the ball's irregular, non-smooth surface may have contributed to the differences between models and the observed data. Now, for the final questions. The model that considers gravity and drag reaches a terminal velocity. This is because the drag force increases and it will eventually be equal to the ball's weight, and as it is opposing gravity, then the net force will be 0, and the velocity will remain constant. However, the model that only considers gravity will never reach a terminal velocity as the force of gravity is not balanced out by any other force. For the what-if question, a paper ball thrown downward would reach the same terminal velocity as a ball dropped from rest. The graph on the left shows the object's velocity once it is thrown downward, and as it is shown in the graph, in both cases the same terminal velocity is being approached. The only difference is the terminal velocity is reached quicker when it is thrown downward in comparison to when it is dropped from rest. Thank you.